I'm going to talk through a connected objects problem. I'll point out some of the main things to look for that you should get every time you set one up. We'll talk through this one. A little bit of a formatting thing. The coefficient of friction is between little m and the surface. Just when I put it on the iPad, it kind of flipped around. How I'm going to solve these is however many objects I have. In this case, I've got 2. I'm going to draw a free body diagram for each object. Push Fnet equals ma as far as I can. Switch to the other object, draw its free body diagram, push that one as far as I can go, and then look for things they have in common. What they will have in common is they're going to accelerate at the same rate. The rope isn't going to stretch, so whatever a value I'm predicting for capital M will have the same a value for little m. And the rope isn't allowed to stretch, so it puts the same force on both objects. Whatever force it pulls m forward with, that's the same force that's dragging little m slowing it, capital M slowing it down. That'll make more sense as we do it. Let's start off looking at capital M, which was 2.5 kilograms. When I draw the free body diagram on it, so those skills we practiced in the last chunk, same sort of stuff is going to go on here. It's accelerating in the vertical component. I've only got 2 forces, gravity pulling it down, tension pulling it up. I'm going to set up Fnet equals ma, just like we did in those other problems, or how I'm always going to do, similar to how I did those other problems. I'm going to think of the forces, and whichever one wins or is larger, whichever direction it's accelerating, I'm going to call that positive. So for this one, gravity is going to win. I'm going to say gravity is the positive force, tension's the negative force, and that's equal to ma. Gravity is always mg minus ft equals ma. In this case, I know that m is 2.5. So 2.5 times 9.8, I get 24.5. Take away ft equals 2.5a. That's as far as I can go with the 2.5 kilogram mass. Going to move on, look at the 1.5 kilogram mass and see what I can get, how far I can go with it. Free body diagram, as always, normal force up, gravity down. We've got some friction backwards, and we've got the rope pulling it forwards. If I start with the vertical, we did some things with angles and inclines, but nothing going on here. So I would call this a boring case. The normal is exactly the same as gravity. In this case, with a mass of 1.5 times 9.8, normal is going to be 14.7. Horizontally, there's a little bit more going on. Turns into an Fnet equals ma situation. This time, the tension is the bigger force. Tension is what's causing this one to accelerate. So I'm going to make that positive. Friction's slowing it down. It'll be the negative, and that's equal to m times a. I don't know what tension is, but I know friction is mu times Fn. It's a boring case, so I know Fn is mg. If I substitute in numbers, the coefficient I had made up for this question was the 0.2 number. The normal force is 14.7, so that cranks out to be almost 3, and that's equal to 1.5 times a. That's as far as I can go with that equation. Now, technically, I'm pretty much done the physics. Now it's going to turn into a math problem. But there are some things I would like you to notice. The tension is the accelerating force on the one object and a decelerating force on the other object. It's a Newton's third law thing. It's always going to be equal and opposite. It's dragging the one object forward, slowing the other force down. So the tension term, that connecting force, is always going to be positive on one of the objects and negative on the other object. What I was trying to say before is the acceleration of the hanging mass numerically is going to be equal to the acceleration of the sliding mass. The rope doesn't stretch, they move. Whatever the hanging one does is it falls. The other one's doing the same rate, the same speeds. It just happens to be moving sideways. The pulley changes the direction but doesn't add any value to those numbers. The rope doesn't stretch, otherwise we might get different numbers. But for now, the connecting force equal and opposite, and they're accelerating at the same rate. This turns into systems of equations from, I believe it's grade 9. I'm going to rewrite both equations. First equation was 24.5 minus tension equals 2.5A. My second equation was positive tension. I'm going to put it over here. Negative 2.94. That's equal to 1.5A. I just like to write it in a different order because it makes it really clear to me. When we set it up this way, our connecting force is equal and opposites, so opposite signs. So system of equations, if we add those two equations, it'll cancel out that connecting force. The 24.5 number and my roughly 3, they make roughly 21.5. The tensions cancel, and that's equal to 4 times A. Flip the 4 to the other side, and we're going to get an acceleration that rounds to 5.4. When I typed this question, I didn't ask about the connecting force, but just like you did in systems of equations, if I needed to know the tension, we could back sub to figure out what the tension was just by substituting the acceleration into either of our equations. That is the method I'm always going to do for connected objects, free body diagrams, F net equals ma, and get two equations and solve that system. That method will work every time. You may be able to look at this and see like a shortcut way. I'm okay with that. Just be aware that sometimes the shortcut way, what works as a shortcut for one question may not work with the